Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we will derive the MGF of a random variable with a geometric distribution. But before we do that, we will obtain a formula that will be very useful in our derivation. Okay, so that's our ultimate goal for this video, solving that problem. But let's talk about that useful result that is going to help us tackle that problem. Okay, so here we go. Let me write it down. Useful result. What we're going to be doing here, right, is obtaining a formula for a particular series. Maybe you have seen it before, maybe not, but I just want to make sure. And anyway, the ideas here, the ideas that we're going to be discussing here are useful. It's fun, you'll see. Anyway, so we will find formula for the following series. So we would like to find a formula for this. Okay, so it's an infinite sum, that's a series, right, of r to the n power. So this would be something like this. R to the power of 0, that's 1, plus r to the power of 1, 2, 3, so on. Okay, so what we're going to do here is first we're going to deal with the finite version of that infinite sum of that series. Okay, so consider the following sum: s equals 1 plus r plus, let me borrow these guys, okay, plus r to the power n minus 1. So this guy, this finite sum, has n terms in it, right? 1, 2, 3, blah blah blah, up to n terms in that sum. Okay, let me call this guy equation 1. Okay, equation 1. Now what we're going to be doing is we're going to be multiplying equation 1 by r. Okay, so multiplying equation 1 by r, right? What we're going to have, let me copy paste this, and I'm going to change that to equation 2. So r times s is the same as r here, and this guy is going to be r squared, r cubed, r to the power of 4, and this is going to be n. Okay, we're just multiplying equation 1 by r. No problem. Okay? Next step. What we're going to be doing is we're going to be computing the difference between these two equations, okay? Equation 1 and equation 2, meaning s minus r times s, this minus this, so we have 1, that guy will survive, but then we have r minus r, those two guys cancel out, r square minus r square, r cube minus r cube, and so on, r to the n minus 1, there's 1 before this guy, and then the only terms that survive when we do that are the first term from equation 1 and the last term from equation 2, right? Okay. Now, let's factor out that s on the left hand side of the equation, so it would be 1 minus r, right? That's exactly the same. We're just factoring out that s and then solving for s, what we end up with is 1 minus r to the power of n divided by 1 minus r. Okay? Okay. Now, important assumption. Assuming that the absolute value of r is less than 1, we're going to take the limit of this expression, because again what we want is a formula for that series, which is the limit as n goes to infinity of s, right? We want to have infinitely many terms. Okay, so here we go. The limit as n goes to infinity of s will be the same, just let me point out that that is just notation. N equals 0 up to infinity of r to the power of n. That's what we want. Okay, but we have this expression in the case of only n terms, so when we take the limit of this guy, the only term in this expression that depends on n is this guy. But if r, right, the absolute value of r is less than 1 when you compute r to the n power, and n is increasing without limit, n is going to infinity, what we end up with is just this. R to the n power goes to 0 if that condition holds, and that's the formula that we wanted. Okay? Okay, so keep that formula in mind, because it will be very useful when we derive the MGF of a random variable with a geometric distribution. So let's go back to our main problem. Let's find solution to that problem. Okay, so we want to find the MGF. Let's start with the definition. So by definition, the MGF of the random variable y is a function of t, is given by the expected value of e to the power t y. Got it? Excellent. Okay. Now remember, again, it's one of the important theorems that we mentioned when we talked about expected values, right? Expected value of g of y, a generic function of the random variable y, is just the sum for all possible values of y of g y times the probability mass function, right? In this case we have a discrete random variable, so the probability mass function, okay, evaluated at the corresponding value y. So in this particular case, for a geometric random variable, right, and remember that there are two different ways of defining a geometric random variable. In this case, the random variable y will represent the number of trials until the first success. Okay, so if that represents number of trials until our first success, we need at least to try once to observe our first success, right? The possible values, the support of the variable y is 1, 2, 3, up to infinity, right? So we have e to the power ty times the probability mass function of y, right? And we said in the case of geometric, we want y represents the number of trials until the first success. So we are going to have 1 minus p to the y minus 1. We have y minus 1 failures, and then at the next step we have our first success, right? Okay, so that's the probability mass function for geometric, right? Now let's try to make this expression nicer. So first let me pull out that p. That guy doesn't depend on y. Okay, so I will pull it out. Okay, now from, I don't know if you remember what we did to derive the MGF of binomial random variable, but it was useful, and this should be a lowercase because it's particular values, not the random variable. Okay, so going back to what I was going to say, I don't know if you remember what we did when we derived the MGF of a binomial distribution, right? But it was useful to have the same exponent here, right? That helped us. So in this case it makes sense that we want to have something like that, because we would like to use our result, our formula for that series we just derived. Okay, so in this case what we would like to have is the same exponent here, right? So how could we make that y minus 1 appear here. Okay. Well, if we multiply by a1, we're not doing anything wrong, right? That's fair game. We're not doing anything illegal. So I'm going to multiply by a very special 1. So e to the power negative t times e to the power of t, that's a 1, right? So multiplying by a 1, that's fair game. Okay? Okay. Now, let me pull that guy out. Okay? That e to the power of t doesn't involve y, so I will pull it out. And then we're going to keep doing some algebra. Let me pull this guy out here. Okay. Now, this e to the power ty times e to the negative t, that's the same as this. Let me rewrite it like this. You agree? That this is the same as e to the ty times e to the negative t, right? Just a little bit of algebra, okay? But now we can just put these guys together and use the same exponent for both of them. Okay? Let's do that. So now what we're going to have is these two guys can be combined, and we could use the same exponent for both of them, right? So these two equations are equivalent. Make sense? Right? Okay, so we're almost there. Let me show you the formula that we derived together, right? Our formula goes n equals 0 up to infinity of something that looks like this, a number to the n power. Again, note that this starts at 0, okay, and goes to infinity. So what I'm going to be doing here is changing variables. Okay, let's see if that helps us, right? Note that when y equals 1, this is going to be 0, okay? Y minus 1 is going to be 0. So let me make the following change of variables. Let n be y minus 1. So now when y equals 1, what we have is that n equals 0, right? And clearly when n goes to infinity, but let's be explicit about it, when y goes to infinity, well, then n goes to infinity as well. Okay, so now let's rewrite that expression. using our new variable n. So we have n, 0, and n, right? So now, using our result and letting r be this guy, right? It's going to be 1 divided by 1 minus r, okay? So it's going to be this p e to the power of t times 1 divided by 1 minus this, right? And let me just make it look a bit nicer. So here we have PET times 1, we have PET, and let me use, instead of 1 minus P, let me use Q, and this would be 1 minus Q times ET, okay? So 1 minus QET. Okay, where Q equals 1 minus P. Okay? Okay. So anyway, this guy here is the MGF that we were looking for. That's the expression of the MGF for a random variable with a geometric distribution. Okay? Okay. So now, again, just like what we did when we derived the MGF of a binomial distribution, let's test drive our MGF to make sure that we got it right. So let's use this expression to find the expected value of y. Okay. Let's find the expected value of y. So again, let me remind you that what we can do if we have the MGF and we want to find the expected value of a random variable, right, is just we take the first derivative with respect to t and then we evaluate it at 0. Okay? So let's do that. Let me rewrite the MGF like this. It's going to be PE to the power of t, right, times 1 minus Q e to the power of t, right, to the power minus 1. Okay, it's the same thing, right? But if I express that as a product, then, you know, when I take the derivative, it's going to be easier, right? Okay, so let's take the first derivative with respect to t. Again, keep that in mind. So let's find the first derivative with respect to t. okay, m prime. So it's a product, so I will find the derivative of a product. It's the derivative of this guy, and I leave that guy as is, okay? No problem. So the derivative of PET happens to be PET, right? So, and I leave the this guy, this factor, the second factor, untouched, okay? No problem. Now, plus, what I need is now this guy as is times the derivative of this factor here. So it's going to be just minus 1, right? 1 minus qt to the power minus 2, right? And by the chain rule, we need the derivative with respect to t of this guy here, 1 minus qet, which happens to be minus qet, right? Okay. So now let's try and do a little bit of algebra. This guy, PET times 1 minus QET to the minus 1 is this guy here, right? So let me copy paste that guy. You guys agree? Okay. Now what we're going to have here is minus times minus 1, that's going to be a plus, so no problem. PET divided by 1 minus QET, the whole thing squared. So it's similar to this, right? Let me borrow this guy and modify it accordingly. So here we said we are going to have a square, this guy here, right? And we have PET times QET, so that's PQE to the power 2t. Make sense? This times this, minus 1 times minus plus, and this is 1 minus QET squared. Are we good? Okay. Now let's try and simplify that expression. The common denominator here would be this, right? So let me borrow that guy. So then what I would have is PET times 1 minus QET, right? So PET times 1 minus QET plus, and this guy, well, that is going to be the same, okay? That one doesn't change. Let's do a little bit of algebra. Let's try and simplify that numerator that we have there. So PET times 1, that's PET, right? And then we have PET times minus QET, that's going to be PQ times E to the power 2t. You guys agree? PET times 1, this guy, PET times negative QET, PQ e to the power 2t. So these two terms will cancel out, and then we will have PET divided by 1 minus QET squared. Okay? Let's copy paste this guy. Let's get rid of these two terms. They cancel out, and that happens to be the first derivative of the MGF of y with respect to t. Okay, first derivative, right? There we are. Okay, now we want the expected value. So what we have to do is evaluate that derivative at 0. Evaluate that derivative at 0. What we end up with is p e to the power of 0, that's just 1, and then in the denominator what we have is the same, e to the power of 0, that's a 1. Okay, now let me remind you that q represents 1 minus p, so what we have here is the same as 1 minus p, but then we have 1 minus 1, they cancel out, minus times minus, plus p, so what we have here deep down is just p divided by p squared, and that is the same as 1 divided by p, and we know that's the expected value of a geometric distribution. Okay, so summarizing, what we did here in this video was obtaining the MGF of a geometric distribution. That's the expression that we obtained. We wanted to check that we got it right. We found the expected value using it, and we ended up with 1 over p, which is what we should have, so we are confident that we did things well. Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.